So we move to the next lecture. It's my pleasure and honor to announce David Spivak from the Topos Institute. He will speak about all concepts are cat, this dash, I don't know. Please.
Okay. Thank you, Bojana. Yes, so this is joint work with Owen Lynch and Brandon Shapiro. Okay, so for the last 15 years, I've wanted category theory to help humanity make sense of its world. So I started out with data migration, where the idea was that differently organized systems need to exchange information. And then I was thinking about operatic compositionality, how you could build new systems from old by arranging them. And then, yeah. Is it recording? Yeah. Did I start over? No. All right. Okay. And then I was thinking about interacting dynamical systems, which is how collectives can act in concert. So I want category theory to help make sense of its world, but then why use math for this? Well, I think of mathematical fields as accounting systems. There are ways that we account for things. There are ways you can give an account of, say, quantities or likelihoods or physical observations or reasoning using an accounting system like arithmetic or probability or Hilbert spaces or logic. So you can account for something and give your accounts and scaffold the way you're thinking using mathematics. So, and math's universality and fine-tuned language leads to this impressive coordination where I can work with somebody in China and I can give them a differential equation to solve, and they can come back and it'll actually work with the thing that I'm trying to do. So this is really an amazing fact about math. We can give these accounting systems that actually work. And then why category theory? Well, category theory is even more finely tuned. The language and principles were designed in the last 70 years instead of over the last 3,000 years. And they're very elegant. And the second thing is that they're constructive. So it's more amenable to tool building and applications. And it's a kind of microcosm of math. It sits within math, but it reflects the structure of all of math, or almost all of math. And I think that what I'm trying to talk about today is that the same story repeats at another level within category theory. It's not going to have everything in category theory, not even close, but it contains a lot of category theory, and it's subsumed within category theories. So the title of my talks was that all concepts are Catsharp. This was a kind of joke, but it's alluding to something in the book Category Theory for the Working Mathematician, which has a section called "All Concepts Are Con Extensions." Now that was an exaggeration. MacLean was exaggerating. Not all category theoretic concepts, let alone all concepts, are con extensions. For example, a category is not a con extension. But it's such a far-reaching notion. It covers adjoints and Yoneda and limits and co-limits. Those three, not so much more than that, but those three, that the exaggeration was worthwhile to him. He was saying, look at how amazing con extensions are. I want to say that the double category Catsharp is similarly far-reaching in the sense that it is not everything. So not all concepts are Catsharp, but many ideas are. So the categories, functors, cofunctors, profunctors, natural transformations, copresheaves and presheaves, elements of a copresheave, parametric right adjoints, nerves of categories, nerves of higher categories, nerves of, monoidal double categories, PolyE for any category E with pullbacks is all in Catsharp, the same Catsharp. You don't have to change it for the E. But not only for category theory does it have all these sorts of things, but it also models dynamic organizational structures like Matteo was talking about his thing today, and org is a kind of sub thing of that. It's used in deep learning, it's used in prediction markets, and many other applications from effects handlers in programming to rewriting, like Chris's talk the other day, data migration between databases, et cetera. So many applied category theory concepts live in the same place, and many category theory concepts live in the same place. So it's elegant, applicable, and far-reaching, so I think it's an important part of ACT, and many concepts live in one space, and the advantage of that is, for example, if you implement this one thing, you will get all of those things. So in this talk, I'll introduce PolyE again, just to make sure that we're all on the same page, and Catsharp. And then I'll show, just to give you some familiarity with it, I'll give you 3 homes for categories inside Catsharp. Then I'll explain how multivariate polynomials and PolyE for an arbitrary category E fit in. I would discuss nerves of categories, because I think that's really cool, but this is applied category theory conference, so I won't talk about nerves. I'll instead talk about dynamic arrangements, and then I'll finally conclude. So dynamic arrangements is the only part of this that'll actually be applied. Okay, so poly. There are many equivalent ways to get poly. So the easiest, one fast way is say, it's the free, completely distributive category on one object. Distributive means that you have products and sums and that they distribute past each other. And completely distributive just means you have more than just binary sums. You have, set array sums and products. So you can take the product of infinitely many objects or the sum of infinitely many objects. So that's one way to say it, free, completely distributive category on one object. Another is, well, there's lots of functors from set to set, and some are called representable functors. They're the easiest ones, maybe. And I'll talk about them in a minute. And these are the full subcategory of coproducts of representables. That's a kind of hands-on way to talk about it. And then a third equivalent way is that it's the full subcategory of all those functors from set to set that preserve connected limits, which are basically like pullbacks and wider span, wider pullbacks. But to bring it down to earth, a representable functor is just something that takes any set x and returns a set of all functions from a to x for some a. So the functor that takes an x and gives you back x squared for any x, that's representable, or x cubed, or x to the fourth, and that's basically all of them, x to the fifth, x to the natural numbers. So those are the representable functors, and coproducts of such things are pretty easy things to think about. They're just like, you take x squared plus x cubed plus 4. Okay, so they're polynomials of sets. The maps between these things are easy by the universal property of coproducts. Everything's just a coproduct of representables. So you use coproducts and Yoneda, and what happens is that you take this coproduct and this coproduct, and you use the universal property of coproduct to pull this guy out. And then you use the Yoneda lemma to plug AI in for Y here. So you get the thing pulled out, you get the sum over J, and you get BJ to the AI to the power BJ, which is the set of functions from BJ to AI. So it's this formula tells you that in order to get a polynomial map, it's kind of a lensy thing. If you saw David Jazz's talk, it says for every I and I, pick a J and J, and for every element of BJ, pick an element of AI. But this category poly has an unprecedented amount of structure. People talk about toposes, it's very structured objects. Poly has a huge amount of structure, maybe more. It just doesn't have a subobject classifier, but it has, and the subobject classifier gives you a lot of great stuff. But it doesn't have that, but it does have a lot of great stuff. So it has all limits and co-limits. It's got a notion of left con-extensions inside of itself. So it's what's called a co-closure to composition. It has 3 orthogonal factorization systems. Someone talked about, who was it who talked about factorization systems? It was Bryce. It has 3 different orthogonal factorization systems, maybe more. It has infinitely many monoidal closed structures. Most people haven't heard of a category with more than 2 or 3 monoidal structures, let alone a category with 2 monoidal closed structures. That's, maybe you've never heard of one. This one has infinitely many monoidal closed structures. It's got free monads, co-free comonads, and lawful interactions between them. So it's just got like tons of structure, which you can use to build all sorts of interesting things. You're constantly able to take something someone's talking about. I noticed I'm able to take, Owen came to me and said, here's what an effect handler is. He showed me some stuff. I rearranged, and we got a very simple definition that actually fits into this talk. So it has many applications in functional programming, in imperative programming, which is kind of the opposite side that usually category theorists don't want to touch, and automata programming like cellular automata or finite state automata. So it's really good for applications and for theory. And one of the first surprising things as we're getting towards this thing called Catsharp is that comonoids in poly are exactly categories. That's just a weird fact. Usually if you take comonoids in something, you expect to get something, but what is it? Well, here the thing you get is called a category, and we're in applied category theory conference. So what's going on there? So if polynomials are objects, then when I want to compose them, like take y squared of y plus 1, if I want to compose those functors, you would get this functor, y squared plus 2y plus 1. But I'm going to write it with this composition triangle symbol to mean I'm feeding q into p. But I'm using that instead of this circle just so we remember that we're not composing morphisms, we're composing objects. Because the functors themselves from set to set are the objects. So you can ask, what are the comonoids and the monoids in this monoidal structure, in this monoidal category here? It turns out that monoids in this are what are called Cartesian monoids are operads, but comonoids are categories. And so if we're looking at, the amazing fact is that they're categories. This is due to Ahman-Uustalu and morphisms. But the weird thing, though, is that morphisms between them are not functors. They're called cofunctors. I'm not going to tell you what those are. Bryce talked about them a bit the other day. So a polynomial comonad is pretty easy to say. And then you work out, just set theoretically, using that formula I showed you, what it means. So what is a comonad? It's a polynomial C, y cubed plus y, let's say. And that'll come up later, that polynomial y cubed plus y. And a map of polynomials, so a natural transformation from that to the identity. And a natural transformation to that composed itself, y cubed plus y of y cubed plus y. Now, how does such a thing give you a category? Suppose I'll tell you how given a category you get such a thing. Given a category for any object in A, write C bracket A to mean all of the maps out of A. Not just the maps to something, but the maps to anything. So over all objects, add up all the maps to those objects. So, right. So this is a big set, all the maps out of A to anything. Now the associated polynomial that I would put here for this category is the sum. I'm supposed to give you a sum of representables. So I give you the sum over all objects in C of y to the power maps out of A. So given an A, what are all the maps out? That's the polynomial. And that weird polynomial that you might never think of, basically, if you look at epsilon, and you looked at that formula I gave you before, you could see that you could put the identity, for every object A, you could pick the identity map out, and that would be what epsilon is. And delta will say for any object and any map out, delta will tell you the codomain of it, and then for any map out of that, delta will tell you the composite. So it's just kind of bizarre if you're looking at it on the screen right now, because it's hard to believe, but categories and comonoids are the same thing. So Catsharp is going to be what we get when we apply Mike Schulman's definition of the comod construction to this. So Mike Schulman said that if you have any double category and it has nice co-equalizers, you can form something called mod D, the monoids and modules of D. And if something, say P for poly, has nice equalizers, then you can form comod P. You can look at the comonoids, and we just talked about comonoids. So any monoidal category you can think of as a vertically trivial double category. A monoidal category you can think of as a bicategory with one object, and therefore you can think of it as a double category. It just has one dot, but it's got lots of things from the dot to itself. And those things can compose, and that's going to be what we're going to think of as P. So P is going to be the one object double category associated to poly. So it's got only one object, it's got poly, many maps from that object to itself, and then we can compose them. And that thing has nice local equalizers. So what that means is it has equalizers for any two polynomials. It has all limits, I said, so that you can take the limit of any pair of maps. And from this, we can form comod P. So we can take Mike Schulman's definition and just run it on P, and we get a double category. And so what double category do we get? Well, we get something that I'm calling Catsharp. And the reason is that by Ahman-Uustalu, the objects are precisely the small categories. So it's got the same objects as cat. But the vertical morphisms in Catsharp are a little bit sharp. Like when you look at the vertical ones, what do I mean by they're sharp? I mean that they're cofunctors, not functors. They're a little surprising. That's what I mean by sharp. So sharp, this notation sharp comes from like algebraic geometry, where you have morphism of schemes, say, or ring spaces. You have a map forward on the topological spaces and then backwards on the sheaves. So I just remember reading Hartshorne and seeing that that sharp notation, and I kind of use that to notate the maps back that you get on for lenses or polynomial functors. Anyway, so it's a kind of way of differentiating it from normal cat. And so we've talked about the vertical morphisms and the objects, and Richard Garner explained in his hottest video that the horizontal morphisms, the bicomodules, whatever Schulman told us we're supposed to do, he says, oh, those are really great things. Those are called parametric right adjoint or prafunctors. These are functors from D sets to C sets. And it turned out that back in like 2011 or 12, I was defining what I thought was the right kind of maps between databases. And those were exactly the maps that I thought were the right kind. So these are the parametric right adjoints. It takes any D set and moves it to a C set in a composable way. So we can take another one from C set to B set or whatever. By every object in C basically gets a disjoint union of conjunctive queries on D. So these prafunctors are more general than profunctors. They're like C-indexed sums of profunctors. So you could say things like, I want all pairs of men with the same favorite book, or women with the same favorite book, or men and women with the same favorite book. Take the union of those three conjunctive queries and pop that into a single table. And that's the kind of way you can move data from D set to C set. And that's the kind of thing that you just get automatically by running Mike Schulman's construction on PolyE, the one object by category, or just PolyE. Okay, so to make Catsharp more palatable or understandable or something, I wanted to show you around a bit. So take you around. What's in this Catsharp thing? So it's an equipment of okay, so here's a very short description. Catsharp is the equipment of comonoids in the distributive completion of one. That's a complete description of Catsharp. And the point is, why would you could say, well, why do I care about distributive completions? Why do I care about comonoids? Why do I care about this sort of thing? Because you might not guess that that's really a great thing, the comonoids in the distributive completion of one. All you'd know is that it has a very short description in classical category theory language. The equipment of comonoids in the distributive completion of one. But it's often a good sign to have a very short description in CT language, because CT language was refined such that short descriptions are not, like shortly describable things are nice. So comonoids in set one times, this is a monoidal category. So you could say, what is Mike Schulman's construction of comod on this? Well, you get span. Or if you take set 0 plus and you take monoids, you get cospan. So we talked about cospan earlier today. Those are also comod equipments or mod equipments. And if you take span and you take the monoids in span, you get prof or cat. So cat, not Catsharp, cat is monads in span, and span is comonoids in set. And so you can that shows that cat also has a really short description. So shortly describable things are pretty nice things, but there's a lot more to say about Catsharp than that it has a short description. And that is I want to give you these three homes for categories. And the first home for categories is the least familiar to you, but the most top of mind for this discussion, namely that they're the comonoids in Poly. So categories are comonoids in Poly. I've said that. I want to keep repeating it because it's so surprising. But you can find functors in this home for categories, but they're kind of tucked away and hardly relevant. It's like, what are functors here? And Todd Trimble gave a talk at the PolyE conference, what are functors? And one way you could say is that every functor shows up as an adjunction in Catsharp. In fact, they constitute the left class of a certain factorization on left adjoints. It's kind of like a terrible way, like functors are very difficult to describe in some sense in Catsharp natively, sitting right there. So that's why I want to give you two better homes for categories, because you want to be thinking about categories and functors, not these new weird cofunctors. Cofunctors are actually really cool. Bryce can tell you how cool they are. I can tell you how cool they are, but sometimes you just want a functor. So the first thing I want to say is that span, the category of spans lives inside of Catsharp as the linear polynomials. So I said that a horizontal morphism in Catsharp is a bicomodule. I didn't quite tell you what that means. It means I already told you what composition was, and a bicomodule is just a polynomial P equipped with a map that way and a map that way, to C composed P and to P composed D. And it satisfies certain laws with respect to like killing off the C variable and stuff like that, using the co-unit and the co-multiplication and stuff like that. But I'm still astounded that this sort of thing, just like a single polynomial with two maps that satisfy some laws, is giving you the information of an entire data migration query that takes any a D set and gives you a C set. More general than profunctors. So profunctors are these things where P is a polynomial with only one, with y to the some power. Okay, so profunctors live in here where this is just a representable. So a single polynomial plus two lawful maps gives you all of data migration. That's pretty amazing. And then bicomodules to 0 are exactly functors to set. So those are the Copri sheaves. Those are just bicomodules from C to 0. And so if you looked at only linear polynomials, what would you get? What if you required C to be a linear polynomial, so it was C times Y? And what if you required all your things here, your bicomodules, to be linear? Then you would get span. And so we can find span as just the most basic part of Catsharp, just the ones with linear polynomials. And then it's well known that monads and span are categories, so we can find span in here, and we can look at the monads and we get cat. So that's the second home for categories. And the third home for categories is that we can. I should probably move a little faster. Here's the category who indexes graphs. Functors from this to set are exactly graphs, and this corresponds to the polynomial y cubed plus y, because this thing has 3 maps out, identity and 2 more, and this thing has 1 map out. And so this is the comonoid. This is the carrier of the comonoid of graphs. And so a graph is just a bicomodule from this little thing, y cubed plus y, to 0. And now prafunctors, parametric right adjoints, might be new to you, but they're really useful. And so path, for example, is a really good one. It's a map from graph to graph, and it sends an arbitrary graph to the graph of all paths in that graph. So that's called a familial functor or a polynomial functor from G to G. And it's well known that path is a monad. So this thing composes itself, maps to itself. And so path is a monad on G, and a path algebra is a category. It's a graph together with a map from paths in that graph to that graph. Any path in me counts as a map in me, or an edge in me. So that's the third home for categories, is that they're the path complete graphs. And that's probably the most familiar way to think about categories. Some people like to think about monads and span, but graphs where you can compose paths is the usual way of thinking about categories. Okay, the most common complaints about Poly are that people know that it's overflowing with structure, but people naturally want more, and their most common asks are, I want multivariate polynomials and you only care about univariate polynomials. Or they yell at me, I want polynomials in E, I want topological spaces, I want measure spaces, I want diffeological spaces, I don't want just sets at the bottom. And so I want to consider both of these at once and look at PolyE for an arbitrary E. This is in the sense of Gambino and Koch and Weber. So if E is a category with pullbacks, you can define this double category PolyE, and the univariate polynomials in it, the ones with one variable, like the ones I'm talking about usually, are just maps in E. And the multivariate polynomials are these bridge diagrams. And so if you took E to be set, what this bridge diagram would correspond to would be J many polynomials in I many variables. And we can find PolyE inside of Catsharp, not inside of some Catsharp sub E, but inside of the Catsharp we already had. So what you do is you take any full dense subcategory of E, you could use E itself. So if E was cat, you could use the 0, 1, 2, and 2 simplices and be done. You find any dense subcategory you want, and then the category of, I'm just going to skip ahead, the category of all multivariate polynomials in E. So we have many variables, we're in an arbitrary E, and now we're embedded into Catsharp by this pattern here. And I'm not going to explain it because I'm running low on time, but it's in the paper. So if you just want multivariate polynomials in set, since 1 is dense in set, every element of every set is a colimit of one element sets, then we can find Poly subset as the full sub double category of Catsharp spanned by discrete categories. So we take Catsharp, we just look, instead of all categories as our objects, we just look at the discrete ones, and we'll find Poly subset in the sense of Gambino and Koch. So we're not scared that we need all sorts of different PolyEs for different E's. We've got them all inside of Catsharp. The last thing I want to talk about is dynamic functions and dynamic arrangements. We often think of functions as machines that take an input and give an output, that are automatic and deterministic and total, and they don't change when you use them. But in real life, machines change as you use them. So the keys on your keyboard, if you use it too much, it might wear off, or your shoes wear down according to how you walk, or your baseball glove gets broken in, right? Or your brain gets, as you use this thing, yes, no matter what you show me right now, I'll respond. It is a function, but what I see from you is changing me. And that's a pretty important kind of computer. And I want to think of that as a dynamic function. It's a function from A to B, but that function depends on the state. And then given a new input A, that's the sort of thing that changes the state. So as I hear from you, as I look at you, that's changing my state. I'm still a function at any moment in time, but the function I am is changing. And so those are exactly the AY, BY coalgebras. So there's an internal HOM. I told you that PolyE has lots of monoidal closures. And so this is one of them. And if I look at this, the coalgebras for this, these are these dynamic functions, functions that change through time. They're also called Mealy machines. But you can do this more generally. So here's the, I've written out why that's true, why AY, BY coalgebras are Mealy machines. But more generally, any wiring diagram is also a map in Poly. This one would be a map from P1 tensor P2 tensor P3, 4, 5 to Q. This picture of wiring is an information flow thing where like positions of this one are flowing into directions of that one or whatever. I probably didn't use that terminology, but these things are information is flowing around like for dynamical systems, et cetera. And that wiring diagram is a map in Poly. If I want that wiring diagram to change based on what flows through the wires, then I'm looking at a coalgebra on this thing, on the internal HOM. So I take P1 tensor P5, call that P, and then the PQ coalgebras are machines that produce wiring diagrams like this, or more general things like artificial neural network weights and biases. And they listen to what flows in and out of this system, and they update the parameters, et cetera, or the wiring pattern based on that. So it's dynamic arrangements. If you wanted someone asked a question about games where what's going on in the game changes the wiring of the game itself, and that's the sort of thing you can do using dynamic arrangements. So you can package all of this into a monoidal double category called org, and org, the point is that org lives inside of Catsharp. Org also lives in Catsharp, and I don't think I have time to tell you why, but it's on these slides if you want to see later. So dynamic arrangements like a baseball glove that can listen to what happens, what inputs you get, and change based on that, like artificial neural networks that listen to the training data and update themselves based on that. Those live in org, but org is a subset of Catsharp. So that's one, I guess once we saw how many different things like effects handlers and rewriting and org and nerve theorems and all these things lived in Catsharp, that's what inspired us to say that all concepts are Catsharp. So I think that having this kind of unified and ready-made notation means that you don't have to constantly be context switching every time you want to learn a new thing. You can see if it fits inside is it a profunctor or a cofunctor or a parametric right adjoint or a dynamic arrangement, or is it a nerve? What is it? And you'll find your Kleisli categories, you'll find your things inside of this thing. So it's a setting in which to do both formal category theory and applied category theory. Thanks.
Thank you, David. Some quick questions, one maybe.
Hi, thanks for the talk. So you relayed this story about someone coming up to you, they told you a concept, Owen, and you did, this, that, and the other thing, and you got it into Poly or Catsharp. Is there a sense in which this process could be regularized or automated and applied to the internet or something?
That would be really cool. I don't know. So what happened was Owen wrote down a big formula, and I was like, oh, that part I could rewrite. Oh wait, now that I have that part I could rewrite. So I did some rewrite rules, and rewrite rules maybe could be those could be implemented. And in fact, with Chris, we did dynamic rewriting and stuff like that. So searching for the rewrite rules could be automated. I don't know about I think searching the internet and doing that automatically is 20 years away or something. I don't know what that is. Who knows what the acceleration? But that feels, it's 20 years away using with AI or whatever. I don't know, feels far to me. But some kind of rewriting theory and searching through possible rewrites could be for. I don't know. I'm bad at technology speeds, but yeah.
Computer algebra system. We could do a computer algebra system for the formal theory of Catsharp.
Yeah, right.
Which wouldn't do what you wanted, but would be cool.
Yeah, I think what you want is pretty science fiction-y right now, but I mean, it should be possible at some point. Yeah.
Let's go to that online question.
Oh.
Is it here? Yours. Okay, the only question, I don't find my mouse. Can you please? Is it yours?
Someone says, thanks, David. Is the duality comonoids instead of monoids, presheaves instead of co-presheaves really essential other than for applications? It's not essential. I mean, comonoids are categories. You can't really, monoids are more like operads. So what are called Cartesian monads are operads. So they kind of switch directions of things. Instead of looking at all maps out, you're looking at you're kind of looking at the inputs of your morphism. I'm not sure if I'm answering your question. Co-presheaves instead of presheaves, that's just a matter of, I think that's maybe a matter of like how you arrange your polynomials, whether you look at maps out or maps in. So I don't think that that's super essential. Yeah.
I'm afraid we don't have time for any more questions. Let's thank David again.